Good morning. Welcome to the third in the NASA Asteroid Grand Challenge Seminar Series. My name is David Morrison. I work for CERVI, the NASA Exploration Science Virtual Institute. I'm speaking to you today from the Lunar and Planetary Institute in Houston, and I thank them for their generosity in giving us this space and this connection. I'm very pleased to introduce today's speaker, Paul Chodas, from JPL Caltech, who is part of the NASA NEO program office at JPL. Paul received his PhD in aerospace engineering from the University of Toronto and has spent most of his professional career at JPL. It's been quite a brilliant career. He is the primary author of the software that has done the orbit calculations, the estimations of impact possibility that are at the core of NASA's effort to understand the impact hazard and to deal with individual potential objects. He did the calculations for the impact of Comet Shoemaker-Levy 9 with Jupiter, and later of the asteroid TC3, which came in and exploded over Sudan, exactly where he said it would. A small anecdote on the Shoemaker-Levy 9, he calculated the impact time apparently very precisely, and then when the astronomers looked, they found a brilliant flash of infrared radiation about 15 minutes after his predicted time. And so some people said he was wrong, they should have known better. What the astronauts were seeing was the bright fallback of material from the impacts into Jupiter. So today, Paul is here to talk about the current status of near-Earth asteroid discovery, orbit calculation, and impact probability assessment. Paul, it's all yours.
Thank you, Dave. Thank you for the very kind introduction. Yes, we were a little bit off on our Shoemaker-Levy 9 calculations, but it was very satisfying to look at Jupiter and see those impact spots right where we had predicted they would be on that planet, and see them even in a small telescope. It was very exciting. So today I want to go over the processes that we follow to discover asteroids, to calculate their orbits, figure out their trajectories, and even figure out the probability that they might impact the Earth. A year ago, we were looking forward to a very interesting encounter of an asteroid called 2012 DA14 that had been discovered a year earlier. And we knew it would come very close to the Earth. In fact, so close that it might pass inside the ring of geosynchronous satellites. And we had been anticipating this for a long time and tracking it, and we knew that it wouldn't hit the Earth. But I put together this little diagram that I think Lindley showed last week that shows that it went actually inside that ring of geosynchronous satellites. Those are the communication satellites and the weather satellites that that hover above a particular longitude on the Earth. And we knew it wasn't going to hit the Earth, and we had this wonderful prediction. We're looking forward to the event, and the whole day, and the NASA broadcast we had that day was preempted by the Chelyabinsk impact, which occurred just slightly earlier. The same day. Now, the DA14 close approach, we had estimated that it was approximately once every 20, 30 years or so, an asteroid of that size would come that close to the Earth, in fact, inside the ring of satellites. The Chelyabinsk impact was also an extremely rare event, on the order of 1 or 2 per century, and happened on the same day. These were unrelated events, but still a dramatic demonstration that rare events can happen on the same day and that asteroids should be paid attention to. Now, I have here a little sample of Chelyabinsk, the piece that entered over Russia. It's a meteorite. It's a stony meteorite. It's fascinating to think. It's just unfortunate that we weren't able to discover this ahead of time and track it and see it coming in, and I'll explain why in a few slides. But this originated from approximately 20-meter asteroid of about 10,000 metric tons, and it caused a 500 kilotons explosion in the atmosphere. You can see the large flare at about 30-kilometer altitude in this photo from a dash cam in Russia that morning. Fascinating event. It demonstrates that we need to keep track of these and discover as many of them as possible. So that was a busy day a few years ago. We have had, the Near-Earth Object Program has had for 15 years a program of monitoring these objects, coordinating the calculations of their orbits, and figuring out whether they could hit the Earth. And I show here just a screen grab of our webpage, neo.jpl.nasa.gov. And the top two stories in this are two asteroids that passed by last week. I'll talk a little bit more about these particular ones and use them as examples. One of them was 2014 EC, and the other one was 2014 DX110. And I'll explain a little bit about the designations in a minute as well. And there's the Grand Challenge announcement right below that. We'll have a few more screen grabs as we proceed through this, but I'll use those two asteroids from last week as examples. Where are the asteroids in general? Well, the large asteroids are in the asteroid belt. So here I've plotted the locations of 43,000 asteroids larger than 5 kilometers. That's all of the known ones, larger than 5 kilometers in size. And here's where they are today. Nicely situated in the asteroid belt, which we call the main belt. You'll see on the left side the leading Trojans that are in the same orbit as Jupiter, and on the right side the trailing Trojans. These more or less stay in formation about 60 degrees ahead of and behind Jupiter. If you look closely, though, there really aren't any large asteroids in the neighborhood of the Earth. The Earth's orbit is in blue in this. So you might say, well, the large asteroids are safely far away. We don't have to worry about them. Only 20 of those asteroids are near-Earth asteroids, NEAs. Now, they also are kind of mixed in with the other asteroids, and they've spent a lot of their time in the asteroid belt as well, as it turns out now. Two of those are called PHAs, potentially hazardous asteroids, and those are, as I'll explain a bit later, asteroids which can come extremely close to the Earth. Okay. What about the NEAs? Okay. The NEAs, here I've now highlighted in the large yellow diamond dots here, the current positions today of all the NEAs with a diameter greater than 1 kilometer. And as you can see, they are well spread out. So there was a big change now from the 5 kilometer limit I used before down to the 1 kilometer limit. As you go to smaller sizes, there are more and more asteroids. And when we talk about 1 kilometer sizes, we're getting a lot of them in the inner solar system. So they are spread out throughout the inner solar system, and we ought to keep track of them. So I'm showing where they are right now, but what are their orbits? Well, their orbits look like this, and I've only shown 300 of their orbits. You can hardly see the orbit of the Earth in this diagram. If I go back, you can see the Earth there on the left and forward. There are a lot of orbits, so how do we keep track of the orbits? That'll be one of the topics that I'll be talking about today. It's a fascinating topic. When you're designing trajectories, as we do at JPL, you have to know all about Kepler's laws. I'll talk a little bit about that. And then we have to worry about all the perturbations that these asteroids could have. Could they come close to any of the planets? Do we take those perturbations into account? I'll be talking about that. How do we find asteroids? NASA funds search programs to look for asteroids and has been very successful at finding the vast majority of asteroids. Currently, there are two major programs, those are the two on the left, Catalina Sky Survey and Pan-STARRS, that are finding the majority of the asteroids. Catalina Sky Survey, in fact, finds about 60% currently. They are the major player in this program. They have two telescopes near Tucson, and one in the southern hemisphere that is not used as much. The two in Tucson are about a 0.7 meter telescope and a 1.5 meter telescope. Let's see, Pan-STARRS is in Hawaii. It has a 1.7 meter telescope. Linear, which is on the right, I show because it is a telescope, a smaller one, which is no longer being used right now. It's being kind of retired, but it found the vast majority of the large asteroids. So it is certainly one of the major players. Let's talk about DA14, though. 2012, DA14. The 2012 is the year it was discovered. The D indicates the half month it was discovered. So D means A, B, C, D, second half of February. and the A and 14 are just a sequence number. It was discovered by an amateur in Spain using very state-of-the-art equipment that not only was a fast readout camera, but it's something that found moving objects that had trails. The asteroid was also found in a less searched region of the sky. He was looking kind of towards the dawn sky and far away from the normal ecliptic area where most surveys look. It was fairly faint, 18.8 magnitude, which is most amateur astronomers can't get that faint, and is moving quite fast. But he found a very interesting object. This is a diagram from the Minor Planet Center that shows the sky coverage of all the asteroid surveys in the last month. Now, at the center point of this diagram is the opposition point, which is the point directly opposite the sun, and the horizontal line is the celestial equator. You'll see that the sky is covered fairly well, but there were holes. Now, during the last month, there was quite a bit of cloud, so we didn't have complete coverage over the whole sky. But ideally, we would like to have the entire sky covered at least once, if not more times, per month. And the different colors in this indicate the dates that the images were taken. And if you look very closely, you'll see that they consist of little mosaic squares. Each of those squares is a field that is the field that the telescope is taking in a single image. The way that the asteroids are discovered is indicated. Oops, yes, the way the asteroids, I'll do that in a minute. The way that asteroids are discovered is by taking a set of images of a given field, let's say 4 images of a field, and then comparing them and looking for objects that have changed position. So that is how asteroids are discovered, optically and by detecting moving objects. So now we'll go to this slide. I wanted to indicate why we didn't see the Chelyabinsk impactor. It was coming from the direction of the sun, which in this diagram is off to the left. It was within about 15 degrees of the direction of the sun. And as you recall from the previous diagram, most of the surveys are looking in the dark sky, that is to say the direction opposite the sun. They move maybe 90 degrees or even farther away from that direction, but they cannot look within 15 degrees or even really 30 degrees as hard of the sun. And the Chelyabinsk impactor was approaching from that direction. So this object could not have been seen on its approach from ground-based optical observatories. Now, if it had had a close approach sometime in the past 15 years especially, it might have been detected. And that is the strategy in the detections we have now. We're looking for objects that are not necessarily on their final impact trajectory. We're looking for objects which may come close once and may impact on a later encounter. So, orbits. Orbits are one of my favorite subjects. Keeping track of these things, what are the laws that they follow? So I have to talk about Kepler's laws, which many of you may have heard of in your introductory astronomy class. But so we're going to start to get a little bit technical, but not too technical, I promise. Kepler's laws are simple. 1, every planet or asteroid follows an orbit which is an ellipse about the sun, and the sun is at one of the foci of the ellipse. Each orbit then lies in a plane because an ellipse is a planar figure, and the plane of the orbit is called the orbit plane, and the plane of the Earth's orbit, which is just another object orbiting the sun, is called the ecliptic. The line joining the sun and the planet sweeps out equal areas of that ellipse in equal times, and the implication of that is that when an object is far from the sun, it's moving slower because there's a long radius arm, and when it's close to the sun, in order to have the same area, it has to move faster if it's to obey this law. That means that even near-Earth asteroids spend a lot of their time out at their farthest points from the sun, typically in the asteroid belt. The third law is that the square of the orbital period of a planet or asteroid is proportional to the cube of the mean distance of the sun. Now, that's a wonderfully mathematical statement. But the implication of that is that the farther away an orbit is, the farther out it is, the slower it will go. So, we go all the way out to Jupiter, which takes, 12 years to go around the sun, Pluto, 248 years, and the Earth 1 year, and then Mercury takes 88 days. That's because it's closer to the sun. So the mean distance indicates how long it takes to go around the sun. The implication of that is that if you have 2 objects which happen to be starting out very close to each other and differ only in mean distance at a given time, and let's say they're circular orbits, then they will, over time, spread out along the orbit because they will have different orbital periods. Their mean motion, as we say, is different, and so they're going to spread out. And we call that effect Keplerian shear, which I may use in later slides, just to indicate that something that starts together is going to shear because they have different mean distances from the sun. Orbital elements. How do we describe an orbit? Well, you only need 6 parameters to describe an orbit. And we have those 6 parameters at a fixed time, which we call an epoch, because, as I'll explain in a minute, those parameters slowly vary. Of the 6 parameters, 2 of them generally describe the shape of the orbit, its mean distance, for example, and its eccentricity. 3 of them describe the orientation of that plane, what direction is the normal to the plane and how is it oriented. So that takes 3 angles. And the final parameter is kind of the angle of where the asteroid is on its orbit. So with 6 parameters, we can describe an orbit. And we don't always use those particular 6 parameters. We can use other parameters, equinoctial parameters. We can use 3 position coordinates and 3 velocity coordinates as orbital elements, although in that case, all 6 of those would change with time. So on the right here, some definitions. The closest point to the sun is called the perihelion distance. You'll hear that used a lot. The farthest point, aphelion distance. And distances are usually measured in astronomical units, AU, where 1 AU is the mean distance between the Earth and the sun. Orbit propagation. So, Kepler's laws do not always hold exactly because there's perturbations on objects. So the gravity of the planets is going to change that ellipse and move it around a little bit. The implication of that is that over time, the ellipse will change. It's not always going to stay the same, and that's especially true if the asteroid is an Earth crosser or any planet crosser. If it comes close to the Earth, that ellipse will change dramatically, as you'll see in a minute. But even if it doesn't come close, the effects of distant encounters and even distant from Jupiter encounters can make that orbit migrate over time. The implication is that over the course of billions of years, we're not going to these orbits are not staying constant; they are evolving with time. Now, the details of the perturbations I've listed that we take into account. We'll take into account the gravitational attraction of the planets when we project an asteroid orbit into the future. We'll take into account the gravity of the planets, the moon, and 16 of the largest asteroids right now. We can up that number in some cases. And by the way, also the gravitational field, the oblateness of the Earth, needs to be taken into account if we're considering a very close approach to the Earth. So I didn't mention that one. Relativity needs to be taken into account over long time frames as well, and precise orbit propagations. And in some cases, we'll also worry about non-gravitational parameters, such as solar radiation pressure and the Yarkovsky effect, which affect asteroids. For comets, we also have to worry about the outgassing. The jet effect that the jets have on comets will move their orbits around and change them significantly. So these are the effects that are influencing the trajectory of asteroids. How do we keep track of it in time? We have to use a process called numerical integration, where we have an algorithm in a computer. We throw in these perturbations in the so-called equations of motion, and then we numerically integrate them forward in time or backward in time to find out where the asteroid is at any given time. We also integrate the sensitivity matrix, which relates variations of the orbital elements at one time to variations in the position or the velocity at another time. And that's important in the orbit determination. So I have a diagram here, kind of hard to see, but I'm showing the asteroid of 2012 DA14, both before the encounter with the Earth last year, which is the outer blue line, and after the encounter, which is the post-encounter blue line. On the upper left, you see where the Earth was at the encounter. That doesn't change. The 2 orbits always come back to the Earth, to their encounter point, even if they are changed. You can see that encounter significantly changed the orbit of this asteroid. And by the way, while I'm on this slide, you can see that 2012 DA14 was given a number, which asteroids are given once their orbits are secure. That is to say, they are known well enough that we can predict decades into the future where they will be. This asteroid is now known as 367943, And then the discoverer of the asteroid, that amateur in Spain I spoke of, has the option of naming it, and he gave it a name Duende, which as I recall, is mythical creatures in Spanish lore. I'm not sure exactly what that. You can look up the precise meaning of the name. So that indicates just to explain the three stages of a designation of an asteroid. It starts out on its very first day with a year and the 2012 DA14, and then once the orbit is well known, it gets a number, and then later on, when an official name is found, then it gets a name. So this one has all three. Let me talk a little bit about the processes that go on when an asteroid is first discovered. This is a kind of a flow chart. It's hard to explain all the steps. Initially, we have a discovery and initial astrometry. Now, astrometry is the measurement of the coordinates of the asteroid on the sky. So this gives an indication to astronomers that an asteroid has been discovered. I'll talk a little bit about that. The Minor Planet Center controls that. The NEO program office here in the middle takes all of the NEO announcements in particular and all of the data on those and computes the trajectories for the NEOs and determines whether they pose any hazard to the Earth. So we have some screening in there because we're also interested in other types of objects, such as mission accessible objects for human exploration. And lately we have the asteroid redirect mission is interested in certain objects, so we'll screen for those and pay special attention to those. A very important piece here is follow-up astrometry. That is to say, once you discover an asteroid, you have a few measurements of it. We don't want to stop observing it. We need to continue to track it. And professional astronomers and amateur astronomers around the world will continue to track asteroids whenever they are bright enough and observable. And so we will accumulate a set of observations over time. The follow-up is very important, and this is a place where amateur astronomers have an important role. The bottom half of this diagram indicates the physical characterization that can go on with asteroids. We can learn about their brightness, the photometry. We'll learn next week about the light curves and rotation rates of asteroids. In the middle, we have visible and IR spectroscopy, spectral types. We'd like to know what their composition is. On the right, we're interested in radar. Radar will give us a very precise orbit because we can use that as in the orbit determination. We can also get the rotation rate. So, optical observations. This is how asteroids are discovered and tracked. So let's talk about that. Most observations we use to compute orbits are optical. The idea here is that a telescope will take a picture of the asteroid and surrounding stars. The image is taken so that it has enough surrounding stars that they are in the catalog. And we know the coordinates of those stars. So we can take the coordinates, let's say one of these streaks on the asteroid, this is 2008 FP. We would take, let's say, the middle of the streak or the two ends and get the times of those when the exposure was taken. And we can compute a precise location, let's say of the middle of the streak, because we know the coordinates of the stars, the catalog stars. We can determine the coordinates of the middle of that streak. And that becomes an observation. The coordinates are right ascension and declination, so they're angular coordinates, kind of the latitude and longitude on the sky of where the asteroid is at that time. Notice that the distance to the asteroid is not known. It's just a point on the sky. We really don't know how far away it is. And when asteroids are first discovered, we haven't really no idea. The largest uncertainty really is in their distance from the Earth. The typical accuracy of these observations is about half an arcsecond. And that's a function of the size of the pixels. Let's say in the CCD image, you can see that there's a little flaring, and you cannot get a perfect observation. So there is some measurement error. And over time, there are dozens, hundreds, or even thousands of observations accumulated for an object, for asteroids like this. And that's how we compute their orbit. Here's an example of the initial observations for asteroid 2014 DX110. This is something we call an MPEC, which stands for Minor Planet Electronic Circular, comes from the Minor Planet Center, which is the coordination clearinghouse for all discoveries and observations. And this is how the world would first know about this asteroid. So we would get our emails in the morning, or we would check online and see that 2014 DX110 had this, let's say, 14 observations. Those 14 lines, each line is an observation. It gives the time. It gives the right ascension and declination coordinates. It gives on the very right let's see if I can even get a pointer. Let's try it. Oh, I don't know whether that's going to work. I'm trying to, oh, here we go. Trying to move the pointer over to the rightmost column. That's not going to work. Never mind. The rightmost column in the top right, you'll see F51. That means this was a pan-stars discovery. The star, by the way, in the leftmost column indicates that's a discovery observation. So this was a pan-stars discovery. We have about 14 observations. And from these 14 lines, we can compute an initial trajectory. And if you go onto our website, and the little news item, I will produce a little diagram of its trajectory. So we can do all the orbit determination we need from an initial set as small as that. Okay, now radar. Radar is used on objects, whether they're newly discovered or long ago discovered objects. Radar is an extremely powerful way of not only measuring their orbit, but also actually imaging the asteroid and seeing what its shape is and that sort of thing if it's big enough. The important thing with radar is that the asteroid's orbit has to be fairly well known, so we need to get if it's a newly discovered object, we need to get enough observations that we can point the antennas accurately enough, and the asteroid has to be within range, because radar has to emit a pulse, and then the pulse has to return, so it's a 1/r⁴ actually is the mathematics explanation for the sensitivity of the radar to the distance of the asteroid. A powerful burst of pulses then is transmitted to the asteroid, and the echoes are then received in a listening window, and images can be made from that. But the most important thing for us and orbits is that we get a precise time delay from the transmission time to the reception time, which is adjusted, by the way, to get to the center of mass of the asteroid. So if the asteroid is large, then we would actually make an adjustment according to where the center of mass would be in time delay, and we'd also get a Doppler shift. So I've made a point there. Radar observations are extremely precise and very valuable at improving their orbit of asteroids. But they're only available in a limited number of cases, and of course the facilities are in high use too. So we have, they can be limited in availability too, but we're getting increased numbers of radar observations, so that's good. Now, this is a little flow diagram, a little bit JPL centric perhaps, where we put the NEO program office in the middle just to indicate some of the things that go on. The Minor Planet Center is our main source of data. They provide observations, identifications, that is to say the names of the object, the designations, the station locations. It's important to model where they are, their initial orbits. JPL gives us data, radar gives us data on radar observations, and the observing community will give us data. Now, what we do in our NEO program office here is we'll fetch the data, and this is done automatically, by the way, fortunately, because there's so many objects. It's done automatically. We will fetch the data, get the observations, get the initial orbits, compute new orbit solutions in the orbit determination, then compute new ephemerides, which means predictions of where the asteroid will be, determine close approaches. We'll run our orbits forward to see when they can come close to any planet, not just the Earth. And then if it can come really close, we'll compute impact probabilities. I'll explain about that in a minute. And then we have a database where we put the orbital elements and these results. On the right-hand side, we also show that we produce a website. I'll talk a little bit about that. Horizons is an ephemeris service that you can log into on our site and find out the elements of the asteroids, compute their ephemerides, and access their various physical parameters. And flight projects are also very interested in our products. So now, a little technical, but we need to talk about orbit determination. That's a subject that's always fascinated me. That is the process of estimating the orbit of an asteroid given a set of observations. It's kind of mysterious in a way because you don't see all you need to know about an orbit. You don't about an asteroid. You don't know how far away it is, for example, when you're observing it optically. So it's kind of a magic process, but the math works out so that you can actually compute fairly indeterminate parameters. The parameters you might think are indeterminate, and you can get fairly good orbits with very little data. The initial orbit estimate comes from the Minor Planet Center. I wanted to point that out. And it's typically based on just those handful of initial observations. For 2014 DX, we had 14, I think, and later on in that impact, you will actually have the initial orbit. I didn't show that. Now, thereafter, orbit determination is an iterative process of refinement. So given a starting orbit, you compute the observations that that orbit implies at the observation times and as observed from those observation locations. And then you will difference what the actual observation is from your predicted observation to get what we call a residual. And we have then residuals for all our observations. We also compute the sensitivity of each of those observations with respect to the orbital elements themselves, which is a big matrix, actually. The next step is to weight those residuals according to their accuracy. Let's say half an arc second is what we think the accuracy of those is. And we combine all of that with the sensitivities in a process called weighted least squares. And out comes a correction to the orbit. That is to say, how far your previous orbit was off. We'll make little corrections to the elements. And then the process repeats until the corrections are small. So that's the basic process of how to compute orbits. Note that every time you have new data, new observations, you need to go through this again. You need to update the orbit. And the bottom point is that the process will also compute the uncertainties in the orbital elements. And uncertainties are very important because that feeds into the impact probabilities, which I'll talk about in a minute. Okay, and here's just a graph of the residuals for the object 2014 DX110 that we talked about earlier and you saw the observations for. And here are the observations reduced to residuals, graphed against time on the horizontal axis. Actually, we're showing more than just the initial observations here, but this was the graph produced last week. What I'm graphing here is the residual and the right ascension coordinate, and the units are arc seconds. So you can see most of the residuals are less than half an arc second, which indicates that those are good data, and that's their expected accuracy. So we think that's an acceptable orbit that produced those residuals. Observations with large residuals would be deleted. We would think, oh, there was some blunder on that, and we're not going to pay attention to objects that lie outside of the majority. A good orbit fit then is indicated by zero mean on the residuals, and we'd like to see no systematic trends, because that would indicate there's some systematic error in the orbit. Here then is a screenshot from our website that is a Solar System Dynamics website, and I'll use it as a starting point for some of the tours of other web subpages to this one that we provide. And I've circled there on the upper left the ways that you can get to if you click those buttons, you can get to a horizon to determine an ephemeris for your asteroid. You can do a small body search, click. I won't go into that, but you can actually search our database on asteroids and look for particular asteroids of different types and get the numbers of asteroids and get complete lists of asteroids that satisfy various conditions. And the small body browser button is one that, let's say we do click that one. I'll show a page on that one later. That's how you get to a particular asteroid. You'll go to a page where you type the asteroid's name in. And there it is. That's the small body database browser page. And I've circled the little box where you would type in the name of the asteroid. I like to type it in with just no spaces, lowercase. 2014 DX110, for example. You type that in and hit enter, and you would actually then go to a page that talks about all the data we have on the orbit for that asteroid. And this is what it looks like. You go there. So here we have the orbital elements for the asteroid DX110, excuse me. And I'm not going to go into the details. On the left column, we have the orbital elements. We have their values, their uncertainties, and the units. The orbital period there of this asteroid, what's that? 1,191 days, for example. The number of observations is on the top of the right-hand column. Only 28 observations in this case, or 4 days for this orbit. And lots of other material. Orbit condition code 7 means it's not particularly accurate. a condition code of 0 means it's a highly accurate orbit, and condition code of 9 means it's a very inaccurate orbit. The lower table indicates its physical parameter, h, which you'll hear about next week a bit. That's the absolute magnitude, and that is based on its measurement of the visual magnitude at the various times. We can reduce then that to an intrinsic magnitude of, in this case, 25.7, and that can be mapped with an assumed albedo to a size. So this is kind of how we get a very rough size of these objects as well. So that indicates kind of what we know very early on any asteroid, really. You can also go, I had circled the button to the orbit viewer. You can call up an orbit viewer for any one of these asteroids, and you can see the elliptical orbit of the asteroid around the sun. And you can view this from different directions with the scroll bars and move it forward and backward in time. That, however, is only a two-body viewer. That is to say, it assumes Kepler's laws. And it is not highly precise and should not be used for precise uses, predicting, for example, far into the future or looking at the details of the close approach. So it's a simple, quick tool to get a general idea of what the orbit is. Let me talk a little bit about orbit uncertainties. And I will have to accelerate, I understand. The orbit uncertainties, the key thing here is that what determines the accuracy of an orbit is the observations, the accuracy of the observations, which contain measurement errors themselves. The ways to reduce an uncertainty would be to obtain more observations, to improve the orbit, to obtain them over a longer time span, the data arc, or perhaps to use radar. The key thing, as more and more observations are made of an asteroid, its orbit is updated, and its orbit uncertainties get smaller and smaller. So that with time, the uncertainties will drop in size. Impact probability is computed, and I'll just go very quickly through how it's done. The orbit uncertainties are represented in position space as an ellipsoid of uncertainty. And we can run that ellipsoid by the Earth through what we call the target plane. And that ellipsoid then becomes an ellipse. And if the ellipse crosses the Earth, as it does in this diagram on the bottom, then we have a chance of impact. And in this case, we had 24% chance for this asteroid impacting the Earth with that ellipse. I won't go over onto all the details, but this involves a propagation of the uncertainties. We can trace the uncertainty region with Monte Carlo points. These are random points that allow us to follow an uncertainty region, and we often do that. On the bottom here, you'll see the uncertainty region, which is quite large for the asteroid 2007 VK184 in 2048. And let's see, we have the Earth pointed out. The moon's orbit is a little circle around the Earth. The Earth's orbit, the moon's orbit is a circle. The Earth's orbit is just a gray line there. You can see some of these uncertainty regions can become very large. That's simply because the uncertainty in the orbit is large. We haven't observed it, let's say, in a long time, and we're projecting it far into the future. So the uncertainties grow with time. Impact probability changes with time. As you add observations, the uncertainties will shrink, and they can shrink onto the Earth, in which case the impact probability would go up. They can shrink off of the Earth, in which case the impact probability would go down. And the warning time here I've talked about is essentially the time before, if you have an impactor, it's the time before impact when it passes a threshold value, let's say 50%. You could use different values of interest in this case. This was a hypothetical impact probability trace I'm showing here, which of an asteroid discovered 40 years before impact. And it may take a number of years and observing sessions before the impact probability rises to even 50%. Keyholes are a complex subject, which we can talk a little bit about maybe in the question period. If you run those Monte Carlos into the target plane, and we did that for Apophis here, you get this cloud of black diagonal lines shown on this diagram. It does not intersect the Earth, so we know it's not going to hit the Earth. But there are locations in that region which could lead to an impact later. So basically, the keyholes are little windows in an impact plane that can lead to impacts in later years. And we have to pay attention to those as well. Now, for Apophis here, the keyhole was only 600 meters wide for the 2036 impact. By the way, this is This is a diagram taken from years ago. The Apophis uncertainty region has shrunk so that it's no longer on that keyhole. But it's interesting, the positions and the widths of those keyholes stay fixed. The size of the uncertainty region may shrink, in which case impacts no longer become possible. Sentry has a risk table that it provides. Sentry is our impact monitoring system, and I just show a snapshot of some of the objects that were on this table last week. The 2014 EC is the second one from the bottom, was also on this list last week. That was a very newly discovered object. This is the impact risk table for that object. It will give a number of possible dates at which that object could impact, all of them with very low impact probability. So, and those impact probabilities went away as the uncertainty shrank. So this is no longer on the Sentry impact risk table. We had a real impact, 2008 TC3 in 2008. This was an object, this is my last topic. It was discovered by the Catalina Sky Survey at 1.3 lunar distances. This is the discovery image. 19 hours before impact. We could compute its impact location. 11 hours before impact was the time we did that. And it was of no concern. We were clearly, the object was small. We knew its intrinsic magnitude. We knew it would be likely break up on entry in the atmosphere. Little impact location, I took out an atlas and circled where the coordinates said it would impact somewhere around Station 6, which translates to Almahata-Sitta, which is now the name for the meteorites which came from this impact. The local time of the impact shortly before dawn, and the impact event was actually observed, and we were a few seconds off. That was because it was a shallow impactor, and it wasn't clear exactly where in the atmosphere the actual detonation would take place. A little trajectory plot and timeline. The circle is the orbit of the moon. At the top is when the object was discovered. I've shown some time ticks as we go along in universal time and made some notes here, the number of observations and what the impact probability was. We knew it was certain to hit the Earth when it was still beyond the moon. The observations finally stopped when the object went into eclipse near the Earth. And on the surface of the Nubian desert, we had predicted trajectory of the asteroid, final trajectory on the atmosphere entry. We didn't know exactly where along the trajectory the asteroid would detonate and release all of the meteorites, but except for that, we knew along the track where it should be, and there's a photo of one of the meteorites found on the floor of the Nubian desert. So the orbit was known very well for that asteroid. We could predict its impact location accurately, and all of the math worked, and it's a demonstration that that the system is working here, and we're able to predict impacts. And with that, I'll stop. Dave, over to you.
Thank you very much, Paul. We have a few questions. Let me start with one that I'm sure you've heard many times. If you predicted an impact, not even necessarily 100%, but an impact just a few days away, would you warn people? And how would the people in the potential impact point learn about it? And what would happen?
Well, certainly that is an excellent question. That is what we are doing this work for. This process was invoked, actually, for this particular 2008 TC3. First of all, we want to make sure we have good data. We want to make sure the observations are good. We want to, if there was an impact in a few days, we would confirm with our colleagues around the world who are also doing similar impact monitoring to make sure that we had the correct information. We then would go to NASA and go to the NASA headquarters and give them the information, and they would then pass that along through government circles. So that is the process that would undertake the political process. The scientific process is that an impact would be issued as soon as the information was set and known. The impact would be published, and the information would be on our website. We would have the orbits, all the information, the technical information would be on our website, and we would then have the impact location could be known ahead of, could be predicted and broadcast ahead of time. It was, in fact, for this TC3 as well. But that all happened so fast, there wasn't really a lot of time to get the information out. But the circles the people who needed to know knew where that would impact. And in fact, we did have some predictions get out in time for a few visual observations from for example, from aircraft.
So you don't have a secret list of dangerous asteroids that aren't on the web page?
No, no. There is no secret list of asteroids. The asteroid data is public. The data is out there. There is a little process where we have to do some technical confirmation. If there is a dangerous or threatening object, there is a process to follow, and NASA and the government needs to be announced, so needs to be notified. So those steps are in there. They can slow down the publication process a little, but the data is out. It's on the web.
What about observations that are made that seem to be real asteroids but are not sufficient to calculate an orbit? Do you throw them away? What happens?
Well, first of all, the Minor Planet Center is responsible for determining whether, when new objects are found, whether there are sufficient observations to confirm the existence of the object. And they have something called the NEO confirmation page, where astronomers know in essentially real time what the list of objects which have been recently observed and are not yet confirmed. They get a list of the objects, and they can go out and look in the sky themselves and look for these objects. When a sufficient number of observatories or sufficient number of days of observations of an object are there, then the Minor Planet Center is responsible for confirming the existence of the object. Tim Spar will have a talk later in the series on that, and that's a good question for him.
You're talking entirely about near-Earth asteroids. What about comets?
Sure, I didn't talk about comets. This is, after all, the Asteroid Grand Challenge. Comets are a wild card because first of all, there are fewer of them. They represent a much smaller fraction of our hazard, on the order of less than 10%, down to a few percent of the impact hazard. But on the other hand, there are wild cards, and we cannot see some of these objects ahead of time. That is to say, if a long period comet could have a period of hundreds or thousands of years and could dive into the solar system, essentially have not, unannounced, and we wouldn't see it in many cases until perhaps a few months before they pass the Earth. So they are a wild card. We can improve our system. Our asteroid surveys, which also look for asteroids, are in fact also finding comets. I didn't mention the NEOWISE, which by the way which is the space-based infrared survey, which by the way found an asteroid just last night. It's also finding comets in the infrared. So yes, we are getting better at finding comets, but they are a wild card, and it is more difficult to get long warning time on comets.
We have some fairly technical questions here. One of them is from an observer who does asteroid occultation work, main belt primarily, and wonders if the uncertainties in predicting occultations are generally due to uncertainties in the orbit or uncertainties in the position of the occulted star.
Oh, that's a very good question. I believe it's largely uncertainties in the orbit, but because it depends on the asteroid, of course, and it depends on how large these uncertainties he's talking about are. But the asteroid orbit prediction uncertainty is usually the largest component of that. That is to say, especially along its track, we may be in error by, as you saw, some of these asteroids have very large errors, but even the well-known asteroids have small errors. So I think the majority of the error is in the asteroid orbit.
Another question, can you recommend a good reference that discusses the propagation of uncertainties in orbit determination?
Wow.
Technical questions, as you see.
A very technical question. There are several books on orbit determination. Boulet is a book that we can provide the reference, Boulet, is a good book on the details and the mechanics of orbit determination. That's one that comes to mind. Andrei Milani has a book on orbit determination, and there are others, more recent ones, which I don't have.
Where can we see the weights you use for the various astrometric stations? Are they the same as the one used by MPC? That is the presumed accuracy of individual observers.
I don't believe the weights themselves are on our website. And the Minor Planet Center generally uses and correct me if I'm wrong, in a few weeks, Tim Spar. The Minor Planet Center generally uses single weighting on all of the observations. The weights are not available online, so that's we don't have an easy way of distributing that information. So we could work together with the Minor Planet Center to find ways of getting that information out.
And here is a question that has interesting ramifications you may want to go into, is how do you eliminate observations of Earth satellites? And I know you recently did work on an asteroid that turned out to be the Apollo 12 or 13 rocket. Can you tell us a little bit about that story?
Sure. That was a story where an asteroid was found by an amateur, actually, and when we computed the orbit, it turned out to be very nearby, and it turned out to be orbiting the Earth. So that's a little unusual. So the first question would be, is that a known satellite? Well, the answer was it wasn't in an orbit of any of the known satellites, and it was quite distant. In fact, it was beyond the moon, so that's not a place where most of the satellites that we know of are orbiting. Let's see. After tracking the asteroid, we could see that there was solar radiation pressure affecting it. So we could see that it wasn't an asteroid, likely, because it was being affected by the radiation pressure, and its orbit was noticeably being perturbed. And that indicates it's not a dense object. That indicates it's more like a can, something very light but with a large surface area. Its area to mass ratio was large, and that's an indicator that we're dealing with an artificial object. And then when spectra were taken, the spectra were found to contain, the absorption lines of titanium paint. So we knew that was an artificial object. Now, the next question was, where did it come from? And I had done statistical analyses of that orbit and ran them backwards in time, which was very inaccurate, perhaps, because it was very chaotic. But it seems that had come, it was in orbit around the sun, and the last time it had an opportunity to be in orbit around the Earth was about the time when the Apollo 12 third stage was left in orbit around the Earth. And so it just put two and two together and concluded that was the Apollo stage. It had the right brightness.
Interesting. Let me just check here. Maybe you can tell us a little more about the evolution of your precision of your predictions. That is, if someone is watching the results on the Minor Planet page, potential objects, and you see month by month or year by year the probability increasing of an impact, should you worry about that? Should we worry about that? The levels of the impact probability have never gotten above I think Apophis was the highest we have seen, which is on the order of a few percent, maybe 5% or so. And that, to me, says that we should not worry about it, because that's a 95% chance that it won't hit. And in fact, that impact scenario, which was Apophis in 2029, after we got more observations, that's what happened. The impact probability fell to 0 for that year. So the outcome in the vast majority of cases is that the asteroid will end up going to 0 probability. So the reason that happens is that initially the uncertainty is large and it can cover the Earth. As we get more and more data, the uncertainty shrinks in our prediction until, depending on where the center of that is or how it's shifting around, it shrinks and it's off of the Earth. And then the impact probability will go to 0. If it happens to shrink onto the Earth, then it would go to 100%. That has not happened. So if I understand rightly, you're saying that the typical scenario is that the probabilities do go up over time and then drop to zero.
The typical scenario is these very low probabilities will go up for a time as the uncertainty region shrinks, and then they will drop to zero. So in almost all the cases, of course, there was the TC3 case when that didn't happen. That was a small case, and it was at 100% almost immediately. But when we're talking about these very low probabilities, especially much lower than 50%, they will fall to zero in most cases. So they will. That's because, as I say, the uncertainty region will shrink and it'll be off of the Earth. So that's the important thing to remember. We'll often say that, the most likely scenario is that the impact probability will go to zero, but and that's the important thing to remember. If it's only when we get up into the many tens, 50%, when we would have to say, well, the most likely scenario is that the impact probability will go to 100%. We haven't had that, except for TC3 when it was 100% almost immediately.
You have been talking primarily about impacts. Are you involved in the search for potential targets for missions to near-Earth asteroids?
When you say missions,
like ARM.
There's
like ARM.
Yes. Okay. So the asteroid redirect mission, if you're asking about that one, yes, we're certainly looking for asteroids which might be candidates for the ARM mission. But the asteroid surveys that are scanning the skies use the same methods to find asteroids of any size and any orbit. So when we augment any survey to find more asteroids, we're going to find asteroids of all different types and orbits. So we cannot target particular asteroid types, or we can't just look for ARM targets and ignore all the potentially hazardous asteroids. It doesn't work that way. When we increase our ability to find asteroids, we'll find them of all sizes, yes.
So bigger and better telescopes will solve all of our problems.
Well, certainly, yes. And I didn't get into the possibilities of future asteroid surveys. Pan-STARRS will have a twin, Pan-STARRS 2, which will be coming online within a couple of years. So that will add capability. The successor to the linear telescope is the DARPA Space Surveillance Telescope, which will begin some operations very soon and be providing, and that's a 3.5 meter telescope. So there are more capabilities coming online. We expect that the asteroid survey capabilities will be themselves of the existing telescopes will be improving over time. So we're getting better and better at covering the sky. It's important to not just cover all of the sky and cover it frequently, that is to say, every few days. It's also important to go deeper, and that is to find fainter objects, and that's more difficult. Spacewatch, I didn't mention, is a telescope that can go very deep and find very faint objects, but it doesn't have a large field of view, so it can't cover a large amount of sky to that depth. The LSST, Large Scale Synoptic Telescope, which will be coming online within a decade, will have great capability to cover large regions of the sky to very faint magnitudes, and it doubtlessly will be finding lots of asteroids as well.
Well, the time is about up, and I don't have any more questions here, but I am sure that some people would be interested to know how big an enterprise this is. How many people are doing orbit calculations? Is there a difference between what you do and what the University of Pisa does? Is this, the equivalent of just a handful of people, or is it a whole army of folks who are working on it?
It's not an army. It's a handful of people. Yes, at the the NEO program office, it's 5 or 6 people that work on all the various aspects that we have going here, and at the University of Pisa, it's also a small group. It's an academic group of just a handful of people. So what we have built are a lot of automation into our systems so that a lot of these processes that I talked about happen automatically, and in most cases, all of the results are presented online. So a lot of it is automated, but there's always new work to do.
Well, thank you, Paul, and congratulations to you and your colleagues. I would like to remind everyone that we now have a full roster of talks every 2 weeks coming up for this spring, and they're all listed on the survey website. And this talk that we just had today will be up and posted within an hour or two. So thank you very much, Paul.
Thank you.